All right, section 16.1, thermal energy and matter. We just got done talking about the differences between potential energy and kinetic energy. Remember, kinetic energy being moving energy and potential energy kind of being the stored energy based on height. When you guys think of energy, you may think of something else, heat. So what the heck is heat? Heat is the transfer of thermal energy from one object to another because of a temperature difference. So heat is the transfer of thermal energy. Heat and temperature are not the same thing. Get that through your noggin. So temperature, what is temperature? Temperature is just a measure of how hot or cold something is based on a reference point. Now that reference point for us is typically absolute zero. I'm going to talk about absolute zero here in a little bit, but heat and temperature are two different things. They're not the same thing. So heat is a transfer of thermal energy based on a temperature difference. Temperature is simply how hot or cold something is. And now, what is temperature? Temperature has to do with the kinetic energy of particles. The higher the kinetic energy, the higher the temperature, the lower the kinetic energy. So kinetic energy is really related to how fast the molecules are moving. The faster they're moving, the higher the temperature. The slower the molecules are moving, the lower the temperature. And at absolute zero, if everything stops moving, at that temperature, everything stops moving, which can't be done, and we'll talk about absolute zero here in a second. So for those of you who are Celsius ignorant, right, which is most of us because we don't live in a world which uses Celsius here in the United States, here's some similarities between the two for you. So on the left-hand side, we have the Celsius thermometer. On the right-hand side, we have the Fahrenheit thermometer. So to give you an idea here, I can move this bar. I'm going to just use one bar. I'm going to get rid of these two bars here. We can move this bar anywhere we go. So for example, 0 degrees Fahrenheit, which is a really cold day for us, is negative 20 Celsius. Freezing, which we know is 32, is 0 degrees Celsius. And a really, really hot summer day in Minnesota, which would be 100 degrees, would be right around 36, 37 degrees Celsius. So Celsius doesn't do a very good job of measuring temperature for weather purposes, but for science purposes it does a fantastic job. Last point I want to point out is Celsius and Fahrenheit. Anyone know when they're equal? Negative 40 Celsius is negative 40 Fahrenheit. That's the one temperature in which they're equal. Gratefully, you guys have not experienced negative 40, I don't think, in your lifetime. So, something to be thankful for. Now, what is something colder than negative 40 Celsius and negative 40 Fahrenheit? It would be absolute zero. So we function on three temperature scales. We function on Celsius and Fahrenheit. You guys know those. And there's a third temperature scale, which is Kelvin. And the reason we have to use Kelvin is because, as we just got done talking about, in the Fahrenheit scale and in the Celsius scale, there are negative temperatures. In the Kelvin scale, there are no negative temperatures, and the coldest possible temperature is 0 degrees Kelvin. So there are no negative temperatures in Kelvin. The coldest possible temperature is 0. Now, what does that convert to in Fahrenheit and Celsius? It's negative 273 degrees Celsius or negative 454 degrees Fahrenheit. All particles stop moving at this temperature, therefore we cannot achieve this temperature. We can only get to negative 453.999999999, repeating. So, absolute zero is the temperature which all motion ceases to exist. It stops moving, the temperature which all motion stops moving. So when we talk about energy and how energy moves and how heat can get moved, which type of matter, think about this, here's your question, which type of matter can transmit energy faster and produce more heat? A gas, a liquid, or a solid? I'll give you 10 seconds. Dun, 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 dun. Dun 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 bum bum dum dum. Got your answer? Answer is a solid. Why in a solid? Because the particles are much closer together in a solid. So here we have a gas on the on the left. We have a gas on the left, a liquid in the middle, and a solid on the right. And which one are the particles closer together? A solid. So when the particles start moving, they're more likely to crash into one another and create heat or transfer that energy. So here in a liquid, you can see that they're farther apart, so they're not going to transfer as much. And in a gas, they're really far apart, so they don't transfer as much. So, all right, solid. Think about it on a cold day. Which feels colder to you almost? On a really, really cold winter day, the air or like the flagpole? All right, the flagpole typically does because that can register the energy faster. Which one's going to heat up faster if you put a blowtorch to them? The air or the flagpole. Usually metals heat up really quick, and that's because most metals are solid and they're able to transfer heat very quickly. Think about it. What heats up faster typically when you're boiling water? The pan, which is made out of a solid metal, or the water? Typically the pan does, right? Because the molecules are closer together. That's why it takes a long time to warm liquid up, particularly water. So, here's a little chemistry for y'all. How do we measure this heat? All right. Here's our equation. Q, specific heat. Q is equal to M times C times change in T. Q equals the heat absorbed. Now, heat is energy, and what was our unit for energy? Our unit for energy was joules. So again, our unit is joules. If I want to figure out the amount of energy that an object might have, or the amount of heat that an object could use based on a temperature change, I'm going to use this equation. Q is equal to M times C times change in T. Q is the heat absorbed, that's measured in joules. M is the mass, which is measured in kilograms. C is the specific heat. This is a constant, and this is different for every substance. Typically, guys, you will be given, actually you guys will always be given this, all right? It's in a table. There's a table that tells you all the specific heats for every substance you ever want to know. You'll be given that. Then lastly, change in T. Now, triangle, we haven't talked about this yet, but anytime you see a triangle in chemistry, it means change in. All right? It's the Greek letter delta. So how do you get the change in temperature? You're simply going to subtract your final temperature from your initial temperature. We are going to work a little bit with this tomorrow in class. We will also do a lab on specific heat. So Q is equal to M times C times change in T. Q is heat. That's measured in joules. M is mass, that's measured in kilograms. C is specific heat, which will be given to you. And change in T is our change in temperature. And we will continue to practice with this equation. However, this is the end of 16.1. This is Mr. Clement, and I'm signing off.